All right, time to get started. It is a huge pleasure to have David Bacon from Google gives today's lecture on Spanner, and looks like we're going to find out not just about all the fun little things in Spanner, including some of its big innovation with TrueTime, but also it's some of the newer things that are happening in Spanner. David, of course, has a rich legacy in technology, got his PhD from Berkeley, working on optimizing virtual functions. He's published over 80 papers, hold 29 patents, worked at IBM. He's an ACM fellow for some of the work that he did on real-time garbage collection. And right now, he leads Google's storage engine teams, which is responsible for over 70% of the total fleet cost for Spanner. So obviously of huge importance for Google as an infrastructure, not just in Google Cloud, but also on regular core Google's business, because F1, which is the revenue maker for Google, runs on top of Spanner. So without much ado, David, the floor is yours. Go for it.
Great. Thank you very much for having me. It's a pleasure to be here. I'm sorry I couldn't be there in person. Um, as I mentioned earlier, the talk has a lot of material. We're scheduled for an hour, but I can stay for half an hour afterwards if people want to ask questions. I'd be more than happy to do that. So I joined Google about almost exactly 10 years ago. Coming to work on Spanner, which I thought I would work on for a year or two. Turns out it's held my interest and fascination for far longer than that. Um, so what is Spanner? Um, Fundamentally, Spanner is a SQL database. So you can do the sorts of SQL operations that I'm sure you're all familiar with by now. So this would be a query to find all the count of all of the artists in our database whose name starts with the letter M. Right. Okay. So anyway, so Spanner is supports external consistency, and I'll talk a little bit later about how the strong consistency was kind of fundamental in Spanner's becoming the sort of really the default storage system for transactional data inside of Google. Next slide. So Spanner is geographically replicated at planet scale. This is an example snapshot that I took of a real database from our visualization tool. So typically we have 3 or 5 replicas. In this case, we have 3 replicas that are relatively close to each other in the US. And that gives us a quorum so that most of the transactions can complete relatively quickly with the local quorum without having to go transatlantic. But we also have multiple replicas in Europe, which gives better latency there. Next slide. So Spanner is a classic horizontally scalable system. So we run anything from a fraction of a server to thousands of servers on each replica that you saw in the previous picture. Next slide. So this is an example of the kind of performance we get with Spanner. Zanzibar is Google's global access control system. So when you, for instance, are sharing Google Docs, the access control all runs through Zanzibar. And you can see here that we're getting 95th percentile latency that's better than 10 milliseconds and 99.9th percentile below 100 milliseconds. And this is for a, distributed full planet scale system. Zanzibar is unusual in that it actually has far more replicas. It has replicas that only serve data and don't take writes, which lets us provide even lower latency, especially in places like South America and Australia. Next slide.
David, a quick
Sure.
question. When you consider the number of replicas and the placement for replicas, you obviously talked about briefly in the previous slide about getting a quorum on a continent, perhaps. Do you also have to worry about regulations in the countries where data is allowed to be stored, or that's not quite important when you do choose a placement for the replicas?
Yeah, we do. And one of the things that has driven Spanner's adoption within Google is that we provide centralized support for that kind of thing. So you can actually store rows within the same database with different geographic placements.
Oh,
So
cool.
I like to say that Spanner is Google's complexity sink. So things like access control and privacy and data residency all get supported in Spanner, and then all of the systems that are built on top of it don't have to implement that themselves, and that's a huge savings in system complexity for the company as a whole.
Great, thank you.
Yeah, next slide. And one of Spanner's big claims to fame is our availability. So you can see here that over the course of 3 years on Zanzibar, we actually maintained our availability significantly above 5 nines. So that's something we are constantly focused on and quite proud of. Next slide, please. All right, so let's talk about scale, because that's always kind of what people think about when they think about Google. Next slide. So at this point, Spanner stores about 15 exabytes of serving data. An exabyte is, what is it, 1,000,000 terabytes. And we're running about 5 billion queries per second. Next slide. So what makes Spanner so big? So you mentioned F1. Originally, Spanner was designed to support F1, which runs ads, which you can see up there. But what's happened over the last decade is that as we have become able to support global transactional consistency at scale, more and more applications and systems have migrated onto Spanner or been built new on Spanner because of the recognition that it just provides a huge amount of leverage in terms of simplicity, right? This is part of the complexity sink. It used to be that each application had its own protocols for dealing with distributed consistency. And now Spanner just takes care of that. And so pretty much all of our billion plus user products now run on top of Spanner.
So David, a quick question over here. When you take one of these applications, I just pick Google Docs as an example. Does this mean the actual contents of the Google Docs that users are creating is also inside Spanner? And what's under that transactional perspective of Spanner? Because I think Google Docs also has a CRDT component to it. So can you map that a little bit better for maybe Google Docs?
So I have a slide on that, a few slides further.
Perfect. Okay, we'll wait for that.
Okay, next slide. So in addition to our external products, Spanner also runs the Google Cloud control plane. So like when you create um, a cloud virtual machine, all of that is mediated through Spanner. We provide Spanner as a service to external customers. And I also mentioned Zanzibar, and then lots of Google's internal infrastructure that we call Google 3 is built on it, storing things like code deltas and all sorts of things. The last I looked, actually I should have looked again this morning, but probably 2 years ago we had, many tens of thousands of databases. It could easily be in the hundreds of thousands by now. Next slide. So this is trying to get at your question before. I think if you were to try to get a sense of Google from a very high level perspective, how we build infrastructure and the way we do data storage, the way I like to think about it is Spanner is Google's metadata, and that metadata is the most reliability and availability critical. It's stored in Spanner. We have 3 or more complete replicas of the data, and we provide global consistency. So Spanner is used to store the web index, the search history, the text of your Gmail messages, the information on your YouTube watch lists, metadata from your photos. Now, as you're kind of alluding to, not everything is stored in Spanner. And in fact, in terms of data volume, Blob Store is far, far bigger. Blob Store is where we store Gmail attachments, YouTube videos, photos. I'm actually not totally sure which things in Drive are stored in Blob Store. I suspect, slides, and I'm not sure about text documents. And for that data, we have normally 2 replicas that are geographically distributed, slightly lower availability, and it's just individual object storage. There's no notion of transactionality there. And then finally, excuse me, a large portion of our storage goes to logs via the Sawmill system. And that has yet lower replication depending on the application. There will be 1 or 2 replicas. It has, yet again, slightly lower availability. Over time, logs often go from 2 replicas to 1 replica. Depending on the type of log, it might also be downsampled as it gets older. So examples of what goes in here are, audit trails, things so that we can make sure that and prove that data hasn't been accessed by the wrong people. Also, every time we run a Spanner server, it's generating log information to standard out and standard error, and that gets accumulated and kept for quite a long time, for debugging purposes. Did that answer your question?
Yes, that did. Thank you.
Sure.
Uh,
So
just one question. I'm sorry to interrupt. Is it okay if I can just the previous slide?
Prashant, do you have a question? Okay. Sorry, David. Go for it.
no problem.
Hey, I'm really sorry.
So I think it's really remarkable.
Sorry, David, we lost you here for a second.
Yeah, it said you muted me.
Oh, no, I was trying to mute. There's another person here, so sorry. Go for it. I have
No
you
problem. So I think it's really remarkable how SQL as a programming abstraction has survived over so many decades and such a massive increase in scale. I talked to some of the people who worked on the original System R system, and at a guess, we're talking about maybe 60 megabytes of data running at something in the order of 20 queries per second, and so that's a 250 million increase in QPS and a 250 billion increase in storage. I don't think there's any other abstraction in computer science that's scaled like that. And I found it funny that the example in the original System R paper was a query to find underpaid programmers. I'm sure they were trying to send IBM a message. Next slide. And in fact, for all this increase in productivity, underpaid programmers have only gone up by a factor of 10x. Next slide. So I think it's also really interesting that we've kind of come full cycle, right? We've started with hierarchical databases, which didn't have really much more structure than a Unix file system. We went to SQL databases with ACID consistency. And those all worked essentially on a single site, even though you had IBM building systems with tightly coupled multiprocessors to scale up the amount of data. So there is really, with the internet, discontinuity where we went from tightly coupled single site systems to suddenly trying to do things at planet scale. And that gave rise to NoSQL and pioneered by Bigtable at Google, which kind of backed off of our abstractions, providing only weak consistency and key value stores. And then finally in Spanner, we've managed to solve those problems of scale and get back to where we were in the 70s in terms of consistency and the high level of abstraction that we're able to program with. Next slide. So, if you look at this trend, right, we've only got 66x growth to get to a zettabyte of data and 200x growth to get to a trillion QPS. So, this is, as I think about the evolution of our system going forward, this is kind of what I'm looking at. Exactly when we get there, 2030, 2033, I think that's well within our fairly near-term future. Next slide. All right, so let's talk a little bit about how Spanner scales. Next slide. So here's an example of a database definition for a table called songs, which holds information about the audio on an album. And, this is, of course, simplified, but it's not that far from the kind of schema that gets used in something like Play or something, Google Play or something like that. And I'm a jazz fan, so you can see there's all of these different jazz songs. But then at the very bottom, we have Gangnam Style, which is the song that quote unquote broke the internet because we used to use 32-bit counters for watch counts in YouTube. Next slide. So basically, what we do in Spanner is we take key ranges and shard them over machines. Here I'm showing just single, in some cases, single rows. Really, each shard is a fairly large key range by itself, but it's enough to distribute the workload pretty well. And so we have this database, and we've sharded it out over 3 different machines. Next slide. And now if people suddenly start listening to Gangnam Style, that row is going to get very hot. And so what happens then is that Spanner will automatically split up that shard and assign it somewhere else to do dynamic load balancing. And we also do merging when we discover that shards are no longer hot. Next slide. One of the key things that we do in Spanner is interleaving. So basically, you can have the albums table and the song table, and you can use that clause at the bottom, interleave in parent albums. And what that will do is it will store the information on disk with all of the songs for an album coming immediately after the parent album key. Next slide.
A quick question on this, David. Is that interleaving done just across tablets in the underlying file system, or within a given tablet, you will actually have rows from these 2 tables that are interleaved at that granularity? What's the granularity of that interleaving on the servers in the storage?
It's on a per row basis in the parent table. So you would have the album row of the parent table would then immediately be followed in the same storage block by the songs of that album, right? And so, this is non-standard SQL, and basically this is just storing data in a pre-joined format, right? And the observation is that, it's highly frequent for there to be kind of a dominant access locality in the system. And so this is pretty fundamental to letting us scale up all of these different applications, right? Gmail interleaves your messages with your user ID, and so on. it's just kind of a repeated pattern.
Great. Thank you.
Next slide. Yeah, so here you kind of, here I tried to kind of diagram how that looks, right? So you see the interleaving. In some cases, we might, like with the All Blues album by Miles Davis, we might actually wind up, splitting things. But for the most part, if you read the parent row, it's very likely that the child, the information in the child rows that you need is going to be in the same block, in which case it's already in RAM, or it'll be in the same chunk on the file server, in which case it'll already be in the buffer cache of the remote machine that you fetched from. So, this gives locality benefits of the kind that every scalable system needs. Next slide. Okay, so I heard that you folks were very curious about true time. It's not my area of expertise, but I spoke to Peter Hochschild, who's one of the inventors of true time. One of the things that's really interesting about Spanner is true time is really fundamental to the way Spanner works. But when the Spanner project was started, that wasn't the case. And the designers were struggling with, how to provide a good global consistency model. And it just happened that the TrueTime developers were sitting very close to the Spanner developers, and they got to talking and, sort of realized that they had the ingredients of a solution. Next slide. So TrueTime is fundamentally based on a technology that gives us, to a very high degree of precision, a coordinated global time. So in each data center, we have these time servers which are using multiple GPS systems to get a coordinated time signal, and then multiple atomic oscillators to act as super high resolution timekeepers. And these two systems provide, so we have multiple oscillators providing redundancy for each other. We have and multiple GPS nodes, and then the two of them kind of act as checks on each other. So the fundamental thing about true time is it doesn't tell you the time, it tells you the range in which the time is. So there's this thing called epsilon, which is the potential error. And when you make a call to true time and you ask, what's the time now? It gives you this interval which bounds both the earliest time and the latest time. And that interval is twice epsilon, which generally is no worse than a few milliseconds and often better. Next slide. So fundamentally, Spanner assigns timestamps to every operation, and it maintains the property that if a transaction T2 starts after T1 commits, then we guarantee that the timestamp of T2 is greater than the timestamp of T1. And in particular, if T2 has some kind of data dependency on T1, we ensure that that invariant is true. I maybe should have mentioned earlier that Spanner is a multi-version database. So instead of just keeping a single version of each value, which is replaced as people update things, we keep multiple versions. And those multi-versioning in combination with this timestamp property means that we can provide global consistent snapshots of the data at timestamps. And we can also do historical reads without having to do any locking, right? Once we're a little ways in the past and know that there are no more updates going on in that time range, we no longer need to do locking to read that data. And that's another feature which is a huge enabler for these, huge systems, right? Like we now have multiple systems with over an exabyte of data just in an individual system. Next slide.
David, one quick question on the historical stale reads. I know the original Spanner paper talked about potentially the read-only query specifying the time or some time range in which they want to read. Is that still how that is done, or is there a different way for the reads to pick which version of the data to read?
Yeah, you can, let's see, you can read at a specific stale timestamp. You can ask it to pick a stale timestamp for you. And then we also have something which I don't think is in the paper, called snapshot epochs, where you can basically take a sort of like you do a stale read and tell Spanner to kind of freeze that data, right? And now you're guaranteed that snapshot, that consistent view of the database won't disappear until you release your snapshot epoch.
Got it. Cool.
And that's another feature that gets used quite a bit.
Thank you.
So Peter has this description of Spanner, in which true time is 40% of Spanner. But I love the way he's just sort of boiled everything down to this very small fragment here. Basically, Spanner does, well, we now have multiple consistency protocols, but originally only did two-phase locking. And so the way the transaction commit flow works is you acquire all the locks, and then you query true time for the time interval now, and you select the latest possible value of the true time interval as the timestamp for the transaction. Then he's reduced decades of work on consistency into this Paxos goop thing, which means we do some kind of distributed agreement protocol. And then we do what's called the commit wait, which you can think of is we just, in a tight loop, we query now until the earliest timestamp of now is less than the latest is less than timestamp, which is the value we assigned from the latest before we did the distributed agreement. And then finally, we release the locks. And the super high level proof sketch is that timestamp is naming an instant when all the locks were held, right? And so that gives us that that ordering. Next slide. So now another key thing here, right, is that because our true time uncertainty is equivalent to 2 times epsilon, right? So transaction latency is almost always longer than the true time uncertainty. And that means that almost always, by the time the Paxos goop finishes, what I showed as this kind of unbounded loop to do the commit wait is only going to do one iteration. And so unless you have the replicas extremely close together, which in most cases we don't allow because Spanner, we have requirements on distribution of things in different failure domains, right? And that means things like, you can't have 2 Spanner replicas in data centers that are close enough that they might get hit by the same hurricane or something like that. And the other thing is that typically you hold locks a lot longer than the true time uncertainty. And that implies, among other things, that if you have a sequence of data-dependent transactions, that's going to limit your throughput of on data-dependent information to 1 over the uncertainty. So if the epsilon is 5 milliseconds, your uncertainty is 10 milliseconds, and you can do I guess that's 100 transactions per second on sequentially chained information. So that is a whirlwind tour through true time.
That's great, David. A quick question on that related to the locking component.
Mhm.
What's the granularity for the lock manager? Is it at the cell level, or at what level do you acquire the locks when you're grabbing all of them at the beginning of the commit protocol?
So it's at, let's see, I don't actually, we use multi-level locking. I don't know the lock manager well enough to say that for sure. I can find out and let you know later on.
That sounds great. Thank you.
Sure. Okay, next. Okay, so let me talk a bit about the storage engine, which is near and dear to my heart. Right, so underneath all of this data sits the storage engine, which is responsible basically for most of the single node operation of the system. Next slide. So in 2014, when I joined Spanner, the system looked like this. We have Spanner was actually developed originally as a fork of the Bigtable code base. And so even though it was providing a SQL abstraction, underneath it all, it was using sorted string tables that were invented for Bigtable to store unstructured data. So that meant that everything was self-describing and enormously redundant, and then we relied on compression to eliminate that or reduce that redundancy when we went to store the information on disk. And obviously this was a great expedience in terms of getting the system up and running, but it wasn't really a good match for what Spanner became. All of that information, each replica stores in the Colossus file system in a series of blocks. One of the things to note is that the Colossus file system itself uses replication to provide a high degree of consistency. When I first got to Google, I was really confused about why we have replication across nodes and then we have replication within a data center. But basically Colossus, being able to rely on the integrity of the local files makes Spanner much simpler, and also means that if there's a single block corruption in a single data center, it doesn't force us to do a remote transaction to execute the query. And then above the layer interface, things are managed as a log structured merge tree, which was also inherited from Bigtable and is used in a lot of large scale data storage systems. Next slide. So with Ressi, which is the name of the new storage engine, we basically, approximately speaking, replaced everything below the layer interface. So that includes the file format, compaction, compression, I/O management, the block cache, the so-called access methods, and what we call mem tables, which are basically the write buffers. This, like I said, when I joined Spanner, I thought this was going to be a quick project. A lot of other people thought it would be a quick project, 2 or 3 years. I think originally 2 years was the estimate. I think the project started in 2013 and we finished converting everything in early 2022, I believe. So it's a huge engineering effort. Next slide.
Did the data format in the Colossus file system also change? And if yes, how did you do that migration?
Yes, it did. It was a radical change because the Colossus format was basically just compressed sorted string tables. And Ressi uses a PAX layout with type-dependent encoding and all sorts of things like run length coding and delta coding. And then we do compression and entropy coding on top of that. I'll talk a little bit more about that later. Next slide. Okay, so this is kind of the question you're asking. How do we swap the engines out? Next slide. So, you know, it's kind of trite, but it really is the classic change the engines of the airplane while you're flying sort of situation, right? We have to somehow switch everyone over while they're running with 5 nines of availability. So, you know, in the good old days when I started working in computer systems in a situation like this, we would send out an email on Monday saying, hey, on Friday at 5 o'clock, we're going to shut everything down. And hopefully we'll be back up and running Monday at 9 a.m. Half the time we weren't up and running again until Wednesday at 9 a.m. So I would say probably at least half of the engineering effort of the new storage engine was around being able to live migrate the system. Next slide. So, you know, not only did we have this huge burden of semantic correctness for this incredibly complicated system, but when you're migrating, you know, the performance envelope of the system, you know, to a certain extent defines what your users consider correctness, right? If you substantially slow down something, you know, even though it's semantically doing the same operations, they will be pushed into an outage because, you know, people won't be able to read their Gmails or whatever. Next slide. I didn't see it advance. I don't know if it's advanced there.
Oh, I was here and I moved over there, but the envelope is now outside the SS table envelope.
Yes, right. Yeah, so, right, so in theory, we want everything to be inside, but in fact, sometimes in certain resource dimensions, it goes outside, even though in other resource dimensions, it's better. Next slide. And then, you know, as I said, there's tens of thousands of databases, each of which interacts with the new system in unique ways. Right, when we started out, even though in aggregate, we took almost the same amount of space as the SS table encoding, there were databases where we were 60% smaller, and there were databases where we were 40% bigger. And, you know, of course, the ones that are smaller silently are happy, and the ones that are bigger are very vocally unhappy. Next slide. And so there's a real issue of velocity here, right? Like how fast can we develop this system while we're doing this with this system that is mission critical, not just for Google, but for, you know, literally billions of people all over the world, right? Like if we took down Gmail, that would be a disaster for many people's businesses and personal lives. So I very distinctly remember after we had our first production outage, or in Google parlance, OMG, and this guy on my team said, oh, I guess the days when we can innovate and change the data structures are over. And that hit me really hard. I was like, we absolutely cannot get stuck in that situation. That'll be a disaster. Next slide. We also had to really struggle with privacy, right? So you know, we're trying to figure out how to debug our representation and improve our compression algorithms. You know, typically the way you would do that is, oh, this, you know, this database has gotten too big. Let's go and look at the data and see what the patterns are. Well, we can't do that, right? We're not allowed to look at people's data. Next slide. And then you've also got right to be forgotten, which means we have this thing called wipeout. So, you know, paradoxically, even though our job is to make sure that data is never lost, we also have to make sure that it gets lost quickly if someone asks you to get rid of it. And those two design points really conflict with each other a lot. Next slide. And then we have data residency, which we talked about earlier, right? So, you know, let's say even get permission to look at some data, like maybe it's a database that we know is storing public information. I still might not be able to copy the data over to my local machine to do debugging. I might, you know, right, like maybe I have to call someone up on the phone and ask, you know, in Europe and ask them to, you know, issue commands on the data or something crazy. Next. So we kind of quickly realized that this is really kind of an interesting experimental computer science problem, right? We want to measure the impact of changes we make on the system. And fundamentally, we need to do that on real data. And we have to do it with a pretty quick turnaround time. We have to do it at production scale, but somehow we have to do it without creating any risk to production. There's a surprising number of OMGs that are caused by experiments. And it has to be statistically accurate and privacy preserving. Next slide. Next slide. So we started out by building a experiment framework that operated on a single tablet. The tablet is kind of a slice of the database, right? And so we wouldn't ourselves look at the tablet, but we'd have a specification of the experiment, read the original tablet, transcode it, and then store statistics about whether we got bigger or smaller. Next slide. And so, you know, we have different experiments to evaluate compression and compaction speed, data integrity. Next slide. And then, you know, to satisfy all of these requirements, we have to be fully isolated from production. So, you know, we made sure that there's no way for the system to write into production, that it continues to work if a tablet gets deleted out from under it. It never stores, it either stores data in RAM or encrypted on disk, but without using any real quota, runs at best effort, so it can always be preempted. Next slide. And then, you know, more things to make sure we don't violate all sorts of requirements. I'm trying to rush through here since we're getting low on time. Next slide. So then we built something that uses Google's Flume infrastructure to do this on all of the tablets in a zone. So this is for a single database. Next slide. And Then we expanded that to something that can launch experiments in all zones where Spanner lives. And now we routinely run experiments on like a 5% sample of our full 15 exabytes of data, which, you know, when I think back to some of the experimental work that I did with, you know, just tiny systems, tiny data sets, still kind of blows my mind. Next slide. This is just an actual screenshot of the kind of information we got. Let's skip that. So can I keep going, or do you want to take up?
Yep, you can keep going, David. You have like 10 minutes more. Go for it.
All right, so I wanted to kind of talk about some open research problems. Hopefully you guys will solve these for us. So I described this experiment framework, and it's great and everything, but you know, Spanner is a highly stateful system, and our experiment framework fundamentally, since we don't write anything, can't model stateful updates. So figuring out how you might do mutating update experiments on a massive scale database in a safe way would be a hugely impactful result. We're playing around with some ideas, but fundamentally, we just don't know how to solve this problem. Next. As I mentioned, we have databases that are have gone beyond exabyte scale. And users actually, you know, following this encapsulating complexity principle for Spanner, users are doing things which conceptually they would like to do as single transactions over, you know, a full database of this size, right? So maybe you want to get rid of URLs from your web index that are more than 30 days old. Or you want to cut the price in half for frequent customers. Once again, we've played with some ideas around this, and you know, the leverage that we have with multi-versioning, I think, you know, potentially makes some sorts of things like this plausible to consider, but once again, no answers for this yet. Next.
So David, just to make sure here, the challenge is you have these transactions that are updating a large number of objects. So probably when you get to the commit time and go grab all the locks, some of them might not be available. So you're constantly aborting these transactions that have large number of mutations and they never get finished.
Right, like, you know, basically you're trying to update 1 trillion rows while people are updating them. So the chance of an abort is essentially 100%.
Yep, makes sense.
Another big issue for us is silent data corruption. So I don't know if you've read any of the papers that I cited down there, but at scale, we can no longer rely on systems, on chips to do what they're supposed to do. And traditionally, people have thought about this as memory corruption errors, but what we have found is that we are actually getting corruptions inside the CPU. So it's performing incorrect operations like incorrectly adding two numbers or jumping to the wrong address or, all sorts of things. We estimate that maybe 1 in 1,000 machines sometimes do this. They're super low probability events, but at our scale, we are seeing this multiple times per week. And so we've had to invest a lot of effort into basically making the system robust to any computation being incorrect. So we're doing this at the system level by checksums on blocks, and at the library level by implementing various forms of checked objects and variables, and currently working on pushing some of these things all the way down into the compiler. But I think this is another fruitful area for research. Next slide. Distributed debugging and understanding of the system. We are still really in the Stone Age, like, I mean, debugging a system like this, I would really like to have some visual console and something that lets me see dependency flows and how information travels. Instead, we're using GDB and printf. Stone knives and bear skins for those of you who are fans of the original Star Trek. Next slide. And then system evolution and migration, right? As I mentioned, a massive amount of effort went into just doing the migration to a new storage engine. We also have situations with people migrating from existing databases into Spanner. And I think this would be a really interesting challenge to see how this could be automated. Next slide. So that's it. I guess I finished with 3 minutes to spare. And so be happy to take any questions.
Great, wonderful. First, we wanted to thank you, David. That was excellent.
Thank you.
Okay, we have time for a few questions, and we can also take it from those who are online. I can start with one. David, when you look through the documentations for Spanner on GCP, there's all this discussion about how you write your transactions, and you have to worry about the number of mutations that you might have in the transactions, and worry about that. How do real life programmers who are not like 5-star Google application programmers, how do they kind of figure out, or is it like I write some piece of code against your API and I hit that limit and I worry about that? How do they break up something that doesn't fit into that number of mutations that you might want to fit into transactions? It's kind of related to what you said. If I've got these long running queries that are doing a ton, but maybe not at that scale, what are practical ways in which people break up transactions?
So I'll have to admit up front, it's kind of weird. I don't get to work with our external customers very much because there's kind of, there's all of these layers between me and them. Whereas internally, if something's going wrong for Gmail, I'll get an instant message and more instant messages if I don't respond to the first one. We actually have quite high limits on the size of an individual transaction. I think it's more rather than the bytes. I mean, of course, there's limits, but I don't know if I can say how big, but it's quite big. I think it's more a question of, how many locks do you have to take? How big, how far does that spread out over the system? We have various tools for seeing what are the hot key ranges of the database, which are the most frequent transactions. So, I think, ultimately, it is maybe the, the least solved problem to kind of tell people, how, how a particular choice is affecting the system. For things written in SQL, you can see the query plan. And there's a query plan visualizer, and it'll tell you, how many rows were scanned and returned at each level of the abstract syntax tree for the query. So often that's a good way to go about it. But yeah, I mean, ultimately there's really a massive surface area of features you can use, right? I mean, we have full text search, we have AI vector similarity search, right? I mean, beyond just the sort of basics of a database. And, that makes it very powerful, but it also means that the interactions can get complex.
Great. Wonderful. I'll ask this question, and maybe that's the final question. Okay. Come on up over here, Basilis, and ask that question. And you may want to just line up here because the microphone's here, so it'll be easier to ask. You can introduce yourself and then ask the question.
Hi, my name's Vasilis. I just had a quick question about one of the things I thought was sort of funny in the Spanner paper. At the very end, you sort of put in there that, a portion of the time that all the Spanner engineers spent was just on like going over people's schemas and sort of, checking them, improving them, and sort of going through that process. Is that something that's still sort of going on as Google's, always sort of scaling, or is that just like, oh, we were just having people port over and?
Yeah, that's a great question. So, I think with 30,000 or 50 or 100,000 databases, right, we have a massive range of sophistication of our users, right? So we have, teams like, Gmail has entire teams dedicated just to analyzing and optimizing their system. But we have small systems where the entire thing is maintained by a few people and they don't have the bandwidth to become Spanner experts. So, there's, we have our own internal documentation. Often groups like the team that does the Google apps, Gmail and Drive and so on, has their own kind of internal guidelines for how they want people to use Spanner. And then we also provide schema review consultation. I think, I wouldn't make that same comment today. I think it's, it's important, but there's now a lot of institutional knowledge about, well, yeah, you have to think about interleaving, and you have to think about multi-site transactions, and so on and so forth. So, it's certainly become a much more widely understood technology.
Sure, thank you.
Wonderful. Thank you. We'll take one last question. Go for it. Do introduce yourself.
Hi, David. Thank you for the amazing talk. I'm Hong, and my question is, I know Spanner runs with Paxos for distributed replication. I know another one of Google's services, Kubernetes, runs with Raft instead. Is there a particular reason? And in general, how do you make decisions between two very similar alternatives?
You mean with concurrency control specifically, or as a kind of general engineering question?
I mean, if you have details into this specific decision, that would be cool to hear, but if not, general is fine too.
I mean, I wasn't around when the decision to use Paxos was made for Spanner. I think we've looked at some of the improvements in that general research area, but so far, haven't seen a reason that, we'd get a really major improvement from making a fundamental change. One of the things that we do at Google is we have kind of this internal resource economy, and every resource is priced in terms of engineer time. So that's the kind of normalizer. So, for instance, a CPU year might be worth, 5% of one engineer year, and a petabyte of disk space might be worth a week of engineer time. I have no idea what the actual numbers are, or I have an idea, but I can't use real numbers. But what that lets us do is, if we're looking at a bunch of projects, right, we'll sort of try to estimate, okay, how much time is this going to take by how many people? And then what kind of improvement will we get in terms of overall efficiency, right? And then we have, teams like search, right? They can actually put a price on, every millisecond improvement in a search query is worth X amount of advertising dollars. But ultimately, the most important decisions often are the ones where you're looking at a new functionality, and then you can gather all the data that you can, but ultimately you need to make a kind of a decision based on your deep engineering knowledge and understanding of sort of where the system technology is going, and where where your external and internal market is going.
Great.
Thank you very much.
Awesome. Thank you, everyone. Let's give David another round of applause.
Okay.
David,
Well,
huge thank you for taking the time. I know your time is super valuable, and hopefully your messenger, you didn't get a message to go put out a fire while you took this time to talk to us. Thank you very much.
Thank you. Thank you for
Take
having
care.
me.
Yep. Bye.
Bye.